All right, we are in the week number 3. That would be the stiffness methods. If you like to find out more information, we have a book that you can read about in the chapter number 14. You don't need to purchase the books. The lecture that I'm providing is good enough for you to complete the assignments or any questions that you have, and I'm happy to help as well. But if you need more information, you can read about it. Now, objective of this lecture. So this is the book that I'm talking about. Now, objective of this lectures to analyze the truss systems. I think last week I already mentioned what is a truss systems. We are using the stiffness methods here, which is the finite element methods, and we're going to use it for indeterminate and determinate structures. Now, today, last week as I mentioned, last week we developed stiffness methods. There was one matrix that we use, and we use the Excel extensively. You know the Excel software, so you don't need to just blindly do the hand calculations, and you know where you're going. You can use the Excel. You can take the help from the Excels. You not always take the Excel first and then you do the hand calculation. No, do other way around. Otherwise, it will be difficult for you in the final exams. Today we're going to talk about the force vectors. Then we do the analysis procedures and we continue our examples. Today I'm going to show you the space gas as well. Space gas software. That is also part of your assignments. I will take you through step by step slowly how to do the space gas software. I hope from the week number 1 I have provided you the link so you can install the space gas software in your computers. You should receive the emails with the download link. If you have no laptop or you did not receive it in our computer lab BG320, we have installed these softwares which you can use it. So let's talk about the force vectors first. Now, what is force vectors? The force vectors has a location here. That force is equal to, let me write the equations for you. Force is equal to stiffness times the displacement. That is the equations that we use. Now, last week in the week number 2, we found this stiffness K. If you remember that last week we found this stiffness K, right? So that's job done. Now this K the stiffness is represented by capital K. Now today I'm going to explain you how you can get the force vectors, and that is represented by Q, and that Q is represented by force vector, and it is a vector. It is not a matrix. This is stiffness matrix, but this is vector. Vector meaning that you have only one columns. So that is the force vectors. That's the name that we are using it here. We have stiffness matrix where you have the 6x6 matrix, 4x4 matrix, and so on. And I will also teach you how to get the displacement vectors. So D equal to displacement vector. Again, it is a vector, and that vectors will be only these vertical one columns only. So today displacement vectors. Now let's talk about the force vector first. Last week we done the stiffness matrix, okay, which is the capital K. This week we're going to do it capital Q, which is the force vectors, and we're going to do the displacement vectors, which is the capital D. Now Q is a global force vectors, as I mentioned, and I explained you global coordinate systems and local coordinate systems last week. The whole truss system has a global coordinate systems, which has a one system like X and Y, and is sitting somewhere 0, 0. That is your global coordinate systems. And you have local coordinate systems. Let's say for these members, you have this is X and this is Y, which is your local coordinate system. So you have a global coordinate systems and you have local coordinate systems. So the vectors that we're going to get it, that will be the global vectors, which is with respect to your X, Y. No one external load. So the truss systems, the truss will be loaded, which has some external load, and the loads always goes onto the joints. Okay, you will never get the load on the members like this. No, it is wrong. It is not a truss. It is become frame. So you have this truss, which is always loaded at the point. So we need to have a no one external load at the unrestrained nodes, and we have unknown reaction force at the support. So when you have a support, like a pin support or roller support, they are unknown forces. They are unknown forces. So for example, 5 and 6 degree of freedom is unknown forces. 3 and 4 is unknown forces. In other words, you can also say fixed degree of freedom and fixed degree of freedoms. You remember last week we done this exercise called fixed degree of freedoms and free degree of freedoms. If you know from the last week, right? So all fixed degree of freedoms are unknown, which are unknown forces. That is another way you can say it. All free degree of freedoms are known forces. I hope it is makes sense. Another one, you can say wherever you have support, that is your unknown forces, and where you can have no supports are the free end, which has a known forces. Known forces. And these ones is unknown forces. Right? So if someone asks me to develop the K matrix, which is quite simple in this regards, because let me show you on the writings. Let me for the last week one that we have these examples last week. You can see the last week examples where we develop the stiffness matrix. Now for the same examples, we have done this capital K, right? You remember that we found this capital K. We found all this, we done this, so we found this capital K, which is we found capital K equal to matrix. Now we need to find the Q matrix. So the Q matrix would be how many Qs that we wanted. We have total how many degree of freedoms? You have 1, 2, 3, 4, 5, and 6. So total 6 rows that we needed. So let me write it down. Total 6. So you have 1, you have 2, you have 3, you have 4, and 5 and 6. I hope you understand these ones. I'm just trying to put those 6. How many total degree of freedom? That many. If you have 10, you put 1 to 10. If you have 15, you can put 1 to 15. If you have um, 6, you can put 1 to 6. So I hope it is makes sense to put the red numbers. Now, out of these ones, because last week we done this freaks and free degree of freedoms. So you can see that this pin is not allowed to move this point in the X directions, and this pin is not allowed to move that one in the Y direction. So it is restricted. It is a fixed degree of freedom. So if I want to put it in that way, that fixed degree of freedoms equal to that is 3 and 4 and 5 and 6. That is your fixed degree of freedom. And free degree of freedoms, which is free. You can see these points can go in the left and right. It can go up and down. There is no any supports at the joint number 2. So here you have free degree of freedom 1 or 2. So if I put more details, free degree of freedoms are known forces. Free degree of freedoms are known forces. So Q1 and Q2 are known. These are unknown forces. That sounds good. So 1 and 2 are known. 3, 4, 5, 6 are unknown. Now what is 1? How many force is going in the 1? There is 0 force going in the 1 because you can see there is nothing going. If someone applying the load here, let's say like this, 3 kilonewtons, you can say that 1 is 3 kilonewtons and it would be minus 3. But there is nothing in the 1, so I can put Q1 equal to 0. So I can put this one first one 0 because there is no force going in the one directions. What about the second one? Yes, there is a force going in the second directions, and this force is opposite because this is positive. This number 2 is going upwards is positive, but this force is going down. And so therefore I can put 2, but it would be minus 2. We don't put the unit, just keep it consistent that we are working on the kilonewtons. So minus 2. And all other forces, which is 3, 4, 5, which is unknown. So we can put Q3, Q4, Q5, Q6. So Q3, Q4, Q5, and Q6. Let me write these numbers in the line 1, 2, 4, 5, and 6. Right. I hope you understand to get the Q vectors. Unmute yourself if you face any difficulties in getting the Q matrix. So let me, we have finished 15 minutes, so which is the good timing now. All right. Let me get these guys here. Copy, Control V. Now, Q1, this is your Q2, this is your Q3, this is your Q4, this is your Q5, this is your Q6. Right? These are all your Q1, Q2, Q3, Q4, Q5, 6. Now, Q1, is there any external force? Let me put these other figures as well. Let me put these figures here as well. Copy. And let's put here. Okay, you can look at these figures here as well, along with our main figures, that you have only the load in these directions, which is where, which is in Q2. So Q2 is going up, which is opposite. So Q2 is -2. Q1, there is no any force going in this direction, therefore is 0. Right? So therefore we put Q1 equal to 0. And this one is a free degree of freedoms. Which ones? 1 and 2. So 1 and 2 free degree of freedom. So it will be no one forces. No one forces meaning it would be either 0 or it has some value. Okay, so when you have free degree of freedoms, I hope you know how to find the free degree of freedom and fixed degree of freedom. When is a fixed degree of freedom? Fixed degree of freedoms. These are your fixed degree of freedom because it has at support. Fixed degree of freedoms. Let's say 3, 4, 5, 6. Then you can put these are unknown. And you can write them Q3, Q4, Q5, and Q6 in these vectors. For the displacement vectors. Let me go back to my lecture notes here. That's okay. Before we going on the analysis procedures, let me go back to the displacement vector. Now the displacement vector is here, which is exactly the similars. Let me get the displacement vectors. Displacement vectors. Now the displacement vector D exactly the same like a Q vectors here. Which is 1, 2, 3, 4, 5, and 6, which are your displacement vectors. Now in the displacement vectors, you will have opposite to these ones. Opposite of these ones meaning you have fixed degree of freedoms and you have free degree of freedoms again. So fixed degree of freedoms, which ones? Again, same 3, 4, 5, 6, 3, 4, 5, 6. And free degree of freedoms are 1 and 2. So here, this is opposite. This is your known displacements. Why? Because you can see these points are fixed. These points are fixed, right? Fixed meaning they will not be moving left, right, or up and down. So they will be 0 displacements here. So all these 3, 4, 5, 6, 0. And this one free unknown because this point can displace in this direction and this direction. So D1 and D2 are unknown, but D3, D4, D5, and D6 are known, which is 0. All these no ones are 0. I hope you understand this ones, which is quite opposite to your no one displacements. So far we done this. Q equal to capital KD. I hope you understand. We done the force vector Q. We done capital K stiffness matrix, and we done the displacement vectors too. So all the students in the positions to get the Q, all the students are the positions to get the K, and all the students are positions to get the D displacements. Once you know these ones, we can use this relationship, which is force equal to Q. is equal to stiffness, which is K times displacement, which is D. Now we can substitute the value that here Q is 0 and -2, Q3, Q4, Q5, and Q6. I hope you understand this, that we just develop this Q matrix, we copy that here. Equal to, we have stiffness matrix. I think the stiffness matrix was here. Let me find it out, the stiffness matrix that we use in our examples. So let's say we have stiffness matrix here. So AE, and this stiffness matrix is this. Now, before we do the stiffness matrix, I like to do the partition of the matrix. The partitions meaning that you have a complete border line between this fourth matrix. You can see 0 and -2, and after that you have Q3, Q4, Q5, Q6, Q7 is starting. So you have 1, 2, 3, 4, 5, and 6. So you have you can see the partitions here. If it is Q3 is not there, Q3 is some value, you can have partition line from 3. So you can see clearly the partition line at 2. So if I put the 1, 2, 3, 4, 5, and 6, and 1, 2, 3, 4, 5, and 6, I can drop the partition line from the 2 as well. So like this. So the horizontal partition line is drawn because you have Q1 and you have Q3, Q4, Q5. And from that horizontal at 2, you can put the vertical 2 as well. Now in here, what I'm going to do it, I will put the value 0.405. I will put the value 0.096. Where it's coming from? That's last week we done this, if you remember that. Now I'm not putting any value here. I will tell you why. I'm not copying it, then you are more than happy to do it in your assignment. And 0.096 and 0.128. There are values, by the way, here. You can see this. Those values are here. Minus 0.33, 0. These values are here. I'm not putting those values there. And I put those values here. And minus 0.033, 0, 0, 0, 4, minus 0.072, minus 0.096, minus 0.096, minus 0.128. These are, we don't need this. We don't write it, these ones. Okay, I hope you understand this. Where I write these all the values, I just write 2 here. And here we put the D matrix, which is you have D1 and D2, and you have these values are 0. So unmute yourself if you not able to do it. Q equal to KD, and draw this line, partition line, 2 by 2 or 3 by 3 or 4 by 4. Partition line not always goes by 2, but it just goes where you have partitions, and we put those numbers, we just substitute that. Okay, before moving on to the next steps. That you are doing it. So for example, let's say I have truss systems, which is look like, let's say I have truss systems. Let's say I have truss systems like this. Now I might have a load here at this point, but I may not have these points. So you might have displacements here, displacement here as well, right? Which is not 0. Only displacement 0 is, let's say 1 and 2. These would be 0. That displacement in these directions is 0 here, and others are not 0. So you just need to look at this one. Fixed.
Like, I got it. So like
degree of freedom.
I have a question. So like you're in the fixed, what do you say? Like
fixed degree of freedom.
Yeah, fixed degree of freedom. In your example, sir, like if you use the truss member, is like the material is kind of like malleable, or it can be easily extendable. Yes, sir. Like if we applied a little force, then it can be extended little bit. Okay, sir. So we can consider the displacement at the fixed support or not, sir?
So at fixed supports,
yeah,
that point, when you
yeah,
have a fixed supports, the
yeah,
particular point is not moving. So
yeah,
when I'm talking about the support, meaning this part can extend.
yeah,
The
yeah, yeah.
truss can extend.
If the material is like kind of not
Hmm.
strong, then it can be extended easily. If we've applied the force
Yeah.
like 10 kilonewton instead of 2 kilonewton, then it can
Yes.
be easily extended. Yes, sir.
Yeah.
Yeah,
That is correct. But
yeah,
there is a one condition: you are not moving this point because is spin. In ideal situations, this
yeah,
point is not going x y. This no point is not going. I'm just talking about the very tiny bit point sitting down there.
yeah. But
So
it can elongate.
the point will not elongate. The member can elongate.
Yeah, member can elongate. Yeah, yeah.
Yeah. So that's the therefore the displacement at this point is 0. But if
Okay,
you're
okay.
talking about the displacement and here, yes, there
Uh-huh.
is not 0.
Okay,
But displacement at this particular point are
okay.
0. At
We're
point.
just talking about the point, certain
Just
point.
talking
Yeah.
about the point.
Okay,
This
all right, sir. Yeah.
D1 and D2, this D3, D4,
Mm-hmm.
D5, and D6 are only the point.
Okay, sir. You got
Point
it,
at
sir.
the support.
Okay, thank you, sir.
But if you are talking very close distance from the point, it is not 0.
Okay.
Got it?
Yeah, yeah.
Okay.
Thanks, sir.
Thank you. So I hope you understand this Q1 Q equal to KD. Now my next job is to find this unknown displacement first, and then we will find the unknown forces as well. So first of all, we have two jobs to do it, because if you look at the whole my systems, if you look at sorry, I need to turn off my camera so it's not pointing the roof. So now if you look at my truss system, all these whole things here on the screen, you can see that this one has a unknown values, which is Q3, Q4, Q5, and Q6, and you have unknown value D1 and D2. So let's start with the D1 and D2 first. Now to get the D1 and D2, so what we do it, we just get this 0 minus 2 equal to AE, and we take this 2 by 2 matrix 0.405, 0.096, 0.096, and 0.128, and then you have D1 and D2. Unmute yourself if you don't understand where it's coming from. Just extracted all these top part Q. This is Q, by the way, but only Q1 and Q2. That is 2 by 2 matrix respectively. That is K, and that is your D1 and D2. That's we can see now you have two equations and two unknowns. Right? So far so good. All right. Now let's forget about AE at the moment. Okay, because AE is given in our examples. We can use that AE in our examples, but let's say we keep it on the side. Now, if you done this inverse of the matrix, so probably you know this, right? A equal to let's say B and C, where A is this one. Let's say this whole part is B and this is your C. So if I want to find the C, I would have A B inverse A. Do you agree with me? Right? Because if you multiply, if you bring this one across, it becomes B inverse. So you understand this, right? A equal to BC, and someone asks you to find the C, you can say that you can bring this one across and it become B inverse. Now you know the inverse matrix, this one. So we have this matrix which is inverse. So let me find that matrix inverse. So let's say I have this matrix which is 0.405, 0.096, 0.096, 0.128. Now to find the inverse matrix, we need to find the dat first. Dat meaning that 0. We just need to multiply the diagonal 0.405 times 0.128, take away 0.096 times 0.096. So I multiply this, take away, multiply these diagonals. So if I use the calculators, 0.405 times 0.128 you get 0.05184, take away 0.096 times by 0.096 times by 0.96, you get 9.216 times 10 raised to minus 3. So 0.5184, take away answers. You get 0.5092. That is your dat. Now, if I want to find the inverse of this matrix, the dat 0.509, and we swap these numbers and these numbers, just change it, and we put the minus sign in front of it. We don't change it, but we just put the minus sign in front of it, right? So that's how we do the inverse, and we just multiply these inside. So 0.128 divided by 0.5092, take away 0.096 divided by 0.5092, and minus 0.096 divided by 0.5092, 0.505092. So in that case, 128 divided by 0.5092, you get 0.251, 0.096 divided by, you get 0.189 minus 0.189, 0.405 divided by 0.5092, you get 0.795. Right, so that is your inverse of this matrix. And if you multiply that inverse by these ones, you will get the answer. So let me multiply. So here you have 0.251, 0 minus 0.189 minus 0.189 and 0.795, and you have 0 minus 2 equal to, and AE, you can just put 1 over AE here. We don't need to worry because it goes another side, which is D1 and D2. So if you can just leave it AE outside, you can just do this 0.251 times 0 plus minus 0.189 minus 2, and minus 0.189 times by 0 plus 0.792 times by minus 2. So you, what happens here? Yep. So 1 over AE, 0.189 times by 2, you got, something is wrong, 0.378, and 0.792 times by 2, you get 1.584. I think I just need to fix it something. Why I'm getting something wrong answers or something. Let me fix it quickly. So if I do the inverse of this matrix, let me find the inverse of this matrix, 0.405 and 0.128, 0.096. So let me quickly do it online, or we can do it on Excel. Excel. Inverse matrix. Excel. What's the command? Okay, M inverse function. Okay, so let's quickly do it on the on these ones. Okay, so what was the values? The values was 0.405, and then you have 0.096, and we got 0.096, and we got 0.128. Right, so that was our matrix, and we want to find the inverse of this matrix. So the command that we will need is first you need to highlight all these four of them. Sorry, you need to highlight this and press equal to m inverse, and then I think you can do this, and I think Control Shift Enter. So you get this. I think I screwed up something. I need to fix that once probably. So I think this is the correct answer. 3 minus 2.25. So let me fix it. I think something wrong here. I will fix it later. So here we got 3 minus 2.25 minus 2.25 and minus 2.25 9.5. 2.25 9.5. Now we can do the same thing here. 3 times 0 plus minus 2.25 times by minus 2, and this one here minus 2.25 times by 0, and you got 9.5 times by minus 2. So let me check. Yep, so that looks good. So here you get 4.5, and here you get minus 19. I need to check my, I think you know how to, if you go back to your school or some stage where you will know how to do the inverse. Like if you get someone give you these 2 by 2, I need to check my maths. Probably something I screwed up. If you look at your maths, probably you need to calculate that, and from that date you can just need to swap those numbers and you can get it that this inverse of the matrix. But I show you the Excel ways as well. So that is your displacements. Displacements equal to D1 and D2. That displacements 1 over AE equal to 4.50 and minus 19. So if you want to calculate D1 equal to 4.5 over AE, and if you know the AE value, that is the displacement minus 19 over AE. And look at the numbers as well. So if you look at the figures, if you look at these figures here, copy. And paste. So you look at this one, D1. Yep, D1 is displacement in this direction, positive, and D2 is going this way, but this is negative, meaning that your displacement is actually here. So what this number is telling me that your D2, which is this ones, would be D2 equal to minus 19 over AE, that's the displacements, and D1 equal to 4.5 over AE. Now, if we know the area, let me check if we have area. Oh, here you go. Let's use the same area for both. They have same area. Oh, just use the same area. I will correct it. 0.06 meters square. Let's say both has the same area, and you have Young modulus. So let's say area equal to 0.006 meters square, and Young modulus is 200 gigapascals. Now you remember that we working length in the meters and load in the kilonewton, or force in the kilonewtons. So here this is good, meters square, but this one is 200 times 10 raised to 9 pascals, meaning that 10 raised to 9 Newton per meter square. Meter square is okay, but Newton is not good. So we can just convert it into kilonewtons. So we get 200 times 10 to the 6 kilonewton per meter square. So we can plug the value. D1 equal to 4.5 over area is 0.06 meters square times 200 times 10 raised to 6 kilonewton per meter square. So if I use my calculators, I might get 4.5 divided by 0.06 times by 200 times 10 to the power 6. You get about very small displacement, which is in meter, 10 raised to minus 6 meters. And if I multiply by thousands, you get in the millimeters, 3.75 10 raised to minus 3 millimeters. Similarly, D2 minus 19, 0.06 meters square, 200 times 10 raised to 6 kilonewton per meter square. So 19 divided by 0.06 times 200 times 10 to the power 6, you get 1.58 times 10 raised to minus 5 meters. And if you multiply by thousands, you get 0.02 millimeters. So I hope you understand how to calculate the displacements in the truss systems using the very simple equation Q equal to KD. And you know how to get the Q, you know how to get the D, you know how to get the Q, and you know how to get the K. And from that, using the matrix inverse, we can do it. The Excel can do the matrix inverse in a 1 second, 3 by 3 matrix, 4 by 4 matrix. But I think with the hands, you also need to know how to do it. I think I will do it. I will show you if I get a times at the end to show you. So first of all, we will write Q equal to KD. Q matrix, I already show it to you how you get it. K matrix, you can get it, which in the week number 2, I already explained you that. And you have D matrix. Now you can draw the partition line. In here, you can clearly see the zone that you have unknown zone. This is a known zone. And this is unknown zone for here. This is unknown zone for here. This is known zone for here. So you get these first two guys here equal to AE. And then you get this chunk here for 2 by 2. And you get D1 and D2. Now, if you get the inverse of these ones, and multiply by these ones, you will get D1 and D2. And inverse procedures given here. Just check on the Googles how to do the inverse of 2 by 2 matrix. They will show you. This just I'm sure that is date. And then probably I done some mistakes here, or I done some minus or something wrong. I can fix it later. And then you just swap these numbers with these numbers and you put the minus sign in front of it. And once you get the dat, you multiply that. Once you get this inverse, you multiply that inverse with this ones by doing this number by this plus these numbers, doing this by this, you will get these displacements. And if the area of the member is given, you can substitute the area of the members and young and force. So you can see that these are unknown forces, Q3, Q4, Q5, and Q6. Q3, Q4, Q5, and Q6. Right? I just write this one again. Q3, Q4, Q5, Q6. In here, I'm going to write those guys. Minus 0.03 E, minus 0.033, 000. And you're going to write minus 0.072. 0.096 minus 0.096 minus 0.096, and you got 0.1, no, minus 0.128, minus 0.128, and you have D1 and D2. So that is D1 and D2. Right. Now we can substitute D1 and D2 here. So Q3, Q4, Q5, Q6 equal to AE minus 0.033, 000, minus 0.072, minus 0.096, minus 0.096, minus 0.128, 1 over AE. D1 is 4 point, here, 4.5 and minus 19. So 4.5 minus 19. We can cancel this. So Q3 equal to minus 0.033 times by 4.5 plus 0 times minus 19 equal to 0.033 times by 4.5. You get here you get minus 0.33. So minus 0.33. So minus 0.33 times by 4.5, you get minus 1.5. Again, look at here. You are applying 2 kilonewtons of force. The reaction would be created here and here would be in this range, right? 1.5 looks reasonable. Q4 0 times 4.5, which is this ones, and 0 times minus 19, so 0. So there is no any reaction force in Q4. Q5 minus 0.072 times 4.5 plus minus 0.096 times by minus 19 equal to, let me substitute that value, 0.072 times by 4.5 minus 0.072 times by 4.5 plus 96 times by 19, you get 1.5 positive. And Q6 equal to minus 0.096 times by 4.5. It's just multiplying horizontally and vertically. Minus 0.128 times by minus 19. So you get 2 kilonewtons. Yeah, so you can stop here and verify your answers. As I mentioned, we don't blindly do it in these ones. You are master students. We don't want you to expect everything follow blindly. We will check equilibrium for you. So in here, the equilibriums, let's say you have a reaction for Q6 2 kilonewtons and is positive. Q6 2 kilonewtons positive. This is 2 kilonewtons. Q5 1.5. Q5 is 1.5 kilonewtons reactions. And minus 1.5 Q3. Minus 1.5 Q3. So you can look at the horizontal equilibrium. So the force in the x direction equal to 0, 1.5 positive minus 1.5, that is equal to 0. So verified equilibrium. Verticals, 2 going down, 2 going up. Again, it is 0 because your truss is sitting one place. It's not in the space. It's not a skateboard. All the force is going in the x, all the forces is going in the y should be matched. So look at this one. These answers that you got it should verify that it looks correct, right? So we calculate the displacements, we calculate the reaction forces. When I pull these pencils by 2 hands, I'm pulling this. Let me put the red arrow here. When I pull these pencils, what kind of force is this? What kind of force is this? Is it the tension or is it compression? I'm pulling it red, left arrow red here, left arrow red here, pulling 2 ends. This is the pencil. Or internal resistance tensions would be like this. Do you agree with me? The blue one, the red one is the external tensile force. But the same time, the blue one is called internal tension force, and that's what we are finding it. Find internal force. Do you all see that one? Or you don't understand the picture? When you apply the force, tensions, then you will get these ones. Similarly, when I have the same pencils and I will push two ends, which is become the compressions, you will get the internal resistance, which are this way. So this is your compression internal resistance. This is your tension internal resistance. Do you understand that? I think in your undergraduate, you study these ones. So now our goal is to find how much internal resistance that you got. Equations that we just need to, we did not put it there. So let me go and find that equations. There you go. That is an equations to find the internal force. And we don't know whether it is in tension or it is in compression. I will tell you when it comes to the story. So this is an equations that we're going to use to find the internal forces, internal axial force. So there you go. This is your equation. So let's say we will do it. Let me member number one. And how do we know where is the member number one? Let me go back. There you go. Copy and paste. So where is the member number one? Look at this. This guy is telling me this is the member number one. So let me draw it up. This is the member number one, and it has a length of, I think the length we get it from our very original figures. It has 3 meters length. It has a length 3 meters. Now, in these equations, area AE we have given, but length is given. Lambda x. Lambda x is we can find it from the element number one. We already found it. You remember this lambda x equal to 1 and lambda y equal to 0. That is handy. Week 2 lectures, we discussed that one. Lambda x equal to 1, lambda y equal to 0. So far, so good. Now we have a location vectors, which is pointing this way. So this is become near node. This is become far node. Do you with me? Because the tail will tell me this is near node and this is far nodes. And the degree of freedoms which I'm going to get is 1, 2, and this is 3 and 4. So 3 and 4. You with me so far? Unmute yourself if any symbols or any directions that you don't have, or any numbers where is coming from, or any points that's where is coming from. I get the element number one, put the length given in the figures, put the near node, far node based on these location vectors, put the degree of freedom 1, 2, 3, 4, and so on. And lambda x and lambda y, we done it last week, and I just get that information. Right. So you with me so far. Now we can use this equation and we plug the value. Near node x, and we have a displacement, by the way. One displacement is here. We calculated d1 and d2. And 4.5 and minus 19. So d1, d2 we calculated is equal to 1 over AE, 4.5 and minus 19. We done it this one, right? So near node, so the equations, let me write these equations. Let's say Q1, small q, is equal to AE on L, lambda x, minus lambda x, sorry. Minus lambda x, minus lambda y, positive lambda x, lambda y, and if near node y, far node x, far node y. right? That's it. Okay, so let's plug the value. Let's keep it AE 3 meters, given in our examples. 3 meters here. Lambda x minus 1, lambda y 0, 1, 0. Near node 1, D1, we got 4.5. We got 4.5, let's say 1 over AE. Y, near node Y, D2, you got minus 19. Far node, because this is fixed point, D3 is 0, right? You remember that, right? Here, D3 is 0, D4 is 0, D5 is 0, D6 is 0. Far node, D3 and D4 are 0. So D3 and D4 far nodes are 0. Let's cancel this. So minus 1 over 3, 0, 1 over 3, 0, and 4.5 minus 19, 0, 0. So minus 1 over 3, we can just do horizontal verticals, times 4.5 plus 0 times minus 19 plus over 1.3 plus 0, 0 times 0. So 4.5 divided by 3 minus 1.5 kilonewtons. Minus sign indicate that is in compressions. Okay. And similarly, we can do Q2. So this one in compression. And if I want you to find it out how you am going to draw it, let me put it. Here you go. And let me put it one more. Okay. Now we have 1.5 kilonewton reaction force going this way. 1.5 kilonewton going this way. Now my questions to you, the red one. Should I put this internal force, which is in compressions, going in these directions? Or should I put these ones going in this direction, 1.5 kilonewtons? Which one is correct way to represent in element number 1, which are in compression, and it is internal resistance? Is the left side or right side? Or let's put 1 or 2. Which one is correct way to represent the internal force, which is 1.5 kilonewtons? And if you choose 1, y, and if you choose 2, y. Understand the questions? That I have a questions. Minus 1.5 minus indicate that is compression force. Minus signs, tension force positive. Now when you get the minus signs, don't worry about it. It's just saying that is a negative, it's a compression force. But how do I put in the diagrams? Which way I should put it? Like how do I present actually in the picture that these are? I don't put negative sign here in 1 and 2. I just put the arrow. That arrow will tell me this compression or tensions, and that will give you the negative force or positive force. No comments. 1.5 compressions. No comments. I will wait for you to think. So, sorry, 1. Let me check. 1. Okay. Anyone else? Why do you say 1? One only. Okay, let me help you. Which one is compression? Forget about the previous one. This one. Forget about this. Let me draw the line just below the red line. Which one is compression? One or that one is the compression, and I'm happy with that one. Everyone knows that. That okay. One is the compressions. Everyone knows that, and that is called external compressions. I like to add one more definition in your brain. When I say compression, it's wrong. I should put external compression or internal compressions. Do you agree with me? That if I put the word external compression, it provides more justifications. When you try to squeeze, let's say you imagine yourself and someone are pushing you from the two hands, like someone is squeezing you, like from your left muscles and your right muscles. There are two guys who are trying to pushing you. You are applying compression load. What you going to do it? You said, get away, go away from me. You are trying to, what you gonna do it? You are trying to resist them in the opposite direction. The internal resistance that will be the opposite of this. Right. So do you agree with me that the blue color one is, do you agree with me that this guy, which is a black one, which is a rod, it has an internal resistance not to be squeezed, don't want to be squeezed. They wants to stay as it is, right? Everyone wants to be positioned in that one. They have internal resistance. So everyone we agree with me that I put the blue one, which is the internal compression force, which is the internal resistance. You unmute yourself that you don't understand the blue color one, that internal compression force. That you are trying to be there when someone doing the red stuff on that black rod. It has an internal resistance to not squeeze. If you keep squeezing, if the red one get more than the blue one, then you will start deforming that members. You will not be able to deform the member. So if you are wants to put the, if you understand the point, that's what I want trying to say. So if you want to put the compression force, which way you put? You can imagine that pictures which I put it to you. I did not show it to you, but I want to imagine that ones. That if you want to put the 1.5 kilonewton, which is the internal compression force, which way you going to put it? One or two? Two. All right. Two. Okay. Now you got a point that why I'm getting these two, which is the internal points that I put it there. So everyone agree that if someone say that put the compression force, internal compression force and 1.5. Well, civil engineering students, you need to know these ones by heart from your undergraduate degree. I don't offend other students, but my civil engineering friends should know these ones in the structural analysis. Did you study the structural analysis? Or not really? All right, so far so good. So this is the internal force in the member number one. Now next target is to get these guys here. And then we will get this. We will get this one. So okay, now member number two. Let's say member number two. Draw it up. Here you go. Member number two. Location vectors. You have 1, you have 2, you have 5, you have 6, you got the length. I think the length we calculated before. The length was element number 2. The length we calculated 5. If you remember that Pythagoras, lambda x and lambda y 0.6, 0.8. So length 5 meters, lambda x 0.6, lambda y 0.8. Right? So let's use the same equations. Q2 equal to AE over L, AE over L minus lambda x minus lambda y, lambda x, lambda y, displacement near node x, displacement near node y, displacement far node x, displacement far node y, AE over L minus lambda x minus lambda y, lambda x, lambda y, near node is because this is your near node. Dash tail is near node. This head is far node. So 1, 2 is a near node. D1, D2, 1 to near node, far node, 5 and 6. So D5 and D6 are far nodes. So EE length is 5 minus 0.6 lambda x minus 0.8, 0.6, 0.8. D1, I think we calculated D1 and D2. You remember that? Here you go. D1 and D2, AE1 over AE 4.5 and minus 19. 1 over AE 4.5 minus 19. D5, D6. If you remember that our here you go. D5 0, D6 is 0 because it's at support. So let me put that 0, 0. These guys cancels. 1 over 5. Let me put this one in. Minus 0.6 over 5. Minus 0.8 over 5. 0.6 over 5. 0.8 over 5. 4.5 minus 19, 0, 0. So minus 0.6 on 5 times by 4.5. Minus 0.8 on 5 plus minus 0.8 on 5 times minus 19. Plus 0.6 on 5 times 0 plus 0.8 over 5 times 0. So let me put that one in. 0.6 times 4.5 over 5. You got you got 0.54 plus 0.8 times 19 divided by 5. That is minus 3 plus 0 plus 0. So you get 2.5 kilonewtons, which is in tensions. Question again. Positive meaning tensions. And before we go, we need to let's get these figures, copy. And copy here. 2.5 kilonewtons. 2.5 kilonewtons. Yep, I'm listening. What happens there? When you have applying these ones tensions, then it will be like this internal. So that is correct answer. So tensors. So I hope you understand the story. If someone asks you to calculate those stuffs, you can easily do it. Now I need to show you these things on the space gas. You can prepare your questions if you don't understand any of these ones. But let me join from my another computers. Have this device. And welcome to do it with me. Probably let me check if it is this. This one comes here. It did not load it yet. So anyway, that's okay. Okay, that is okay. All right, now you remember that we done these examples. Let me show you that examples here. You remember these examples we done it. basically this example, determining the force in the each member of the two member trusses, so on in figures. So we calculate the displacement here, we calculate the reaction force, and we calculate the forces here. We can do it everything in the space gas softwares with you, and we can verify our answers with the space gas softwares, and we can comment it on that one. The space gas software that you see, they use exactly the same methods that we teach you. They use stiffness methods. Behind the screens, they are doing this one. So we not only teaching you these methods which are not relevant. No, all the software that you're going to see with me right now, it is built on these stiffness methods. The equations and all these displacements and all Q and F and D that you see, it is based on these displacements methods. Okay, very simple softwares, nothing so fancy about it. Anyone can learn it. Just follow the instructions. I will show you some instruction here. This is the new buttons. If you want, you can put the new buttons. If you want unit somewhere, if you go to these structures here, and if you put the unit, it will have a length in millimeter, section property in millimeters, material strength in megapascals, density in here. If you want to change it, change it. Don't change it for our subjects. Keep it this constant. But in the futures, if you are working in the industry and someone wants to use different property, you are more than welcome to do it. You can just change it feet, inch, or whatever the property that you seems require. Yeah, so otherwise you need to remember that. But for our case, we keep it these ones. This one's load in kilonewtons, moment in kilonewton, mass is this, and length in meters, and section property. Keep in mind, or let me, for your records, let me get this snap here so we can refer it back. We press OK. I'll just show you this one. Don't touch it, this one's okay. Otherwise, it will give you the answers differently. When you okay, so that is the unit stuff. On here's I will show you one by one. You can go to the structure and you can go to a structure wizard, and there are standard beam, standard frame that is available, that if you click on here, they will just appear windows, and you can put pin supports and roller support and so on. That's the one way that if you have standards one. So that's let's cancel this. Let's cancel this. So there is a standard version, or you can draw it by yourself. Screen. These examples, I am changing the slides as well. Examples here. Okay. We are here now. We have this origin here 0, 0. That's the origin that we're going to start with. Now, member number one is horizontal member. So if I have 0, 0 here, if I have 0, 0 here, this coordinate would be 3, 0. Do you with me? Because in the x-axis it is 3, and in the y-axis it would be 0. So you agree with me that if I want to draw this one 0, 0, then what you do it, you go here, draw nodes, no, draw members. Click on draw members. Click on draw members. Don't press anything in your keyboard. Don't do it anything. Sometimes you may pick something else, but it has a highlighter. You can pick it, but I generally don't do it. I press 0 in the keyboards. Enter X, Y, and Z location 0, and hit OK. Keep it to horizontals in these ones, and you press 3 in your keyboard and enter. And you can click the exit button. You can use the zoom like a middle mouse buttons to just get it on here. Otherwise, you can do this view probably somewhere. You need to exit from your one, and you can just use that your middle mouse button to just expand it more. So this is a 3 meters members that we just draw. From this point, this is 0, 0, and this is 3. This is another point. Unmute yourself if you fall behind. What I done? I click draw members. I did not do nothing. I press 0 in the keyboards. Keep the horizontal, and I press 3 in the keyboards to make it these 0 to 3 meter long members, which is exactly the same that you see. Now we draw these members. Second members that is going from this point, which is 0, 0, to this point, which would be 3, across and 4 up. So coordinate here would be 3, 4. So let's draw that once. From this point, we are going here. Draw members. Put the 0 in the keyboard. And then in your keyboards, we can put I think we cannot put the coordinate 3. Yep, you can put it 3, 4, right? Because X, Y, and Z is 0, so you don't need to put it there. And hit OK. So there you go. OK, so something looks good. So 3 meters. And this one is 4 meters from here to here, and this is 3 meters. OK, that is the coordinates for this ones. So what we done so far? We done 3 meters, and we take 0, 0 again, and we draw 3, 4 the across. And this is meters because you can see in our length is in meters. So nothing so complicated. If you want to, because you can see this command is active, the member command is active, you just press the escape buttons on that ones to escape from. So I don't have any commands active. Otherwise, the command before was active. The draw member command was active. So that's what we done. We take 0, 0, we draw it, we take this with coordinates. Unmute yourself if you don't understand to draw this one. Here you have pin supports at here and you have pin support at here. So in here, everyone agree with me. When you go close to this point, it will just come back to the green round. Click on here, single click or just escape, just double click. Just when you highlighted green, click double click. You have different restraint. Restraint means boundary conditions. It has no restraint at the moment. It is fixed. There are let me explain you those letters. So those letters, there are 6 letters you can see. Sorry, you can see F, 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 F. So the first 3 letters stand for displacements. Displacement in the X, that is the first letter. Second F is the displacement in the Y, and third F is displacement in the Z. Remaining 3, the fourth one or remaining 3 is for rotations. So if you have fourth F, which rotation about the x-axis is fixed, rotation about y-axis is fixed, and rotation about the z-axis is fixed. So that's the meaning of fixed F. Everything is fixed, meaning that there is no any rotation allowed. There is nothing like a fixed support. So if I hold something very tight, the point, I'm talking about point again. The student asked me a question. You remember that we need to have this is point. I'm talking about that point is fixed in all directions. There is a pin here that is fix all the displacements. You can see first 3 displacements are fixed. There is a rotation fix about the x-axis, but the rotation about the y and rotation about the z is allowed. And z-axis is coming out of this screen. OK, that is a z-axis. X is horizontals, y is this ones, and the z is out of the screen. So there are 2 rotation allowed. There is a roller supports here as well. So basically, we're going to use these 3. We're not going to use these. We're not going to use these. Probably this will also not be useful. So I think we're going to use all these 3s. OK, but you are more than welcome to think about what they're talking about. Free and fix and all. OK. All right. So we are here. So let's put this pin and hit OK. Now you can't see this pin that we done it. So what you do it, you come back here and show the node restraints. So when you show the node restraints, it will show you that is pin. Now in the students will tell me, oh, look at the pin. Your pin is going like verticals, and in our figures, the pin is like this way. No, the intention is to this point is fixed. This point is not going X or Y. It doesn't matter if you put the pin this way or pin this way or pin this way. This is just a presentation. So you can put the pin this way. So there is no any issue. This is same things. Again, double click on these ones, and we have pin here. Click on here pin and hit OK. If you can't see the pin, you always show the restraints, not show the restraints. So it is better to show the restraint at the start, so you will see what is happening. You following, we draw it and we provide the restraint. That's the first things that we done. Right. So now let's do the next one. That next one that we have 2 kilonewtons coming down here. So at this point, there is when you click on these ones, I think there is a button called, yep. So when you click on these ones, these guys will activate. Look at this. This guys is on is not active, but when you come on this one and click on this origin, it will highlight it, node load. Click on the node load and the window will appear. Do nothing here. You don't need to do it anything here. Just hit OK. And our load is in the y directions, y force, because you have x force, y force, z force, and the kilonewton. So if I show you in the figures, this is x force, this is y force, z force is coming out of the, we don't have z force. So we have y force and is going down. So we need to put -2. In the software, going up is positive. So we put -2 to show that it's going down. And hit OK. Don't do anything. Hit OK. Hit OK again. And you can see this arrow going down. You're not seeing that arrow. So you can hide this. You can check this and hide this origins if you like. And if you can't see the number, then you go here and show diagram annotations and hit OK. And you can see -2 kilonewtons. Going down, -2. So doesn't matter. You can put the load first and then you put the restraint. The sequence is not important, right? It's the software will recognize that you have -2 kilonewtons. These are fixed. So you can put the load first and then you put the restraints after. So that's pretty much it. OK, there are few steps. There is ones in your, and I give you the link as well already, right? That EMS5CAE software. You can install it in your computers. Otherwise, it's already installed in our computer labs. So we put the restraint, we put the loads. Now, next, we can put the boundary condition. Sorry, the material property. Now, if I go back here, we have a Young modulus 200 gigapascals, but we have material property in megapascals. You can see material strength in megapascals. So of course you can come back here and change this one to gigapascals, or we can put it in the megapascals. So if you have gigapascals, if you want to convert it into the gigapascals, let me show you that one, conversions. So someone give you someone give you 200 gigapascals, and we want how much megapascals, right? We want how much megapascals. You want how much megapascals. Now, megapascals. So if you know the gigapascals is 10⁻⁹ pascals, right? Now, if I want that one, so that would be megapascals would be 10⁶ pascals, right? So if I want these ones, I would have let's see, 200 thousand megapascals, right? That's how it become. This ones becomes, I think, if you divide it by thousands, then you are in the position to convert these ones into these 200,000 megapascals. So let's put this 200,000 megapascals as a Young modulus. Where is it? Material here, and we put the Young modulus 200,000 megapascals. What else we needed? We need to put the area. So if you go back here in this book, or we can just click on this 3 dot. Sorry, we go on this book and let me see. or we can just put the area here. Area. If you go to this T, this you know this T, and then let's put the square, and you want to put the area. Let's say 10 by 10, and then we just change that area because that is in millimeter square. So how much millimeter square you might get it? You have 0.006 meter square. So you have 0.006 meter square. We want in the millimeter square. So 0.006 times by 1000 times by 1000 again to get it into the millimeter square, because 1 meter square is this. So you get 0.006 times 1000 times 1000, you get 6000 millimeter square. Millimeter square. So let me put that one 6000. So here we can change it this ones to 6000. Right. So megapascals 6000 millimeter square and hit OK. If you want to see, you can just click on these ones and you will be able to see those members size. Otherwise, we just keep it on the wireframe. And you don't need to do it this one, second one. Otherwise, you can, if you have a different cross sections, you can do a second one. But I think once you've done the first one, it will have all the properties. We don't touch it, these I and A and alpha and everything. Just we need this Young modulus, and we just need this area. All right, so that's so far so good. Anything else? I think we don't need anything. And you do the analysis, linear static analysis. If you do it everything okay, then static analysis completed in 0 minutes. So it is successfully completed. OK, now if you want to see the results, displacement here minus 0.022 millimeters. That's what we found, right? You remember that? Why displacement 0.002? Yep, I know. All right, so minus 0.02. I think we done the hand calculations. It's not appearing. It's on my other computers, but that has a 0.02 millimeters. So you can compare your hand calculations with this 0.02 millimeters displacement. So that's button here to show the answers. OK, we put it back. Now, someone said, what about the reaction forces? We can put those reaction forces. You remember that minus 1.5 going this way, 1.5 going this way, 2 kilonewtons going up. If you want to clearly see, I remove that one. So you can see clearly 2 kilonewtons going up, 1.5 kilonewtons going this way. That's our you remember Q2, Q3, Q4. I can show it to you. Here you go. Q3 minus 1.5. So Q3 minus 1.5. How come this is Q3? You can see 3 here. So that's how you see 1.5 going this way. 0. There is no 0 here. Q4 0, because you can see the fourth one 0. Q5 1.5. Q5 1.5 going this way. Q5 1.5 going this way. Q6 is 2, 6 here, and is 2 going up. Q6 going up 2. So you verify displacements, you verify the reaction forces. Now you want to verify your internal forces. There you go. Minus 2.5. Remember, you calculate minus 2.5 tension force here, and we calculated 1.5 internal forces. You remember that, right? I can show it to you here again. That we done these calculations. You remember Q1 AE over L minus 1.5 compression force. You remember that compression force theory. We done it for 1, and that is your compression force. They draw above the line to show that is positive, and this space case software used the compression as a positive, tension force as a negative. So they draw line below this one, so it doesn't matter. It's just an assumptions, but in our lecture notes we use compression as a negative, but that's pretty much the assumptions that they make it. So they use negative as a tension. So that's tension force here. If you want to clearly see, you can put those details. So we verify how much displacements you got. we verify how much reaction force you got, and we verify how much internal force. So we verify when you do the hand calculations, you can verify your answer. And all this calculation that is performed by the space gas softwares is done exactly. They done the programming, and that programming metrics and all that's done the performance and calculation and give us the answer.